Yeah, I'm very happy to get the opportunity to present our work here. My name is Nico Leuze. I'm with the Institute for Applications of Machine Learning and Intelligent Systems at the University of Applied Science in Munich. And yeah, I will give you a short introduction on our work for scan pattern adapted voxel partition in which can be used for several deep learning approaches for 3D perception. And as a start, I want to give you some introduction or motivation in our work. Here one can state that the recent advancements in several high-tech areas, such as autonomous driving, robotics, crowd analysis, that rely on a thorough 3D understanding, that these areas demand for high quality 3D information, large detection ranges, which has forced LiDARs to become indispensable devices for these areas or modern 3D perception. And especially solid-state LiDARs are gaining great interest in research and industry, since solid-state LiDARs neglect large moving parts, which allows comparatively low cost, and enforces the tolerance against environmental disturbances. Despite these advantages, point clouds are relatively hard to process, especially for deep learning tasks, since point cloud data is unstructured and suffers from 3D sparsity and is non-uniformly dense. On solution approaches for that problem, I will come back later. What I further want to introduce is that really important requirement for several applications is the accurate and reliable detection of people. And besides the named challenges that are associated with the processing of point cloud data, a viable crowd analysis is particularly a problem, since diverse movement patterns suffers from occlusions and are further often really small for sensors to capture. And that given, I can sum up our research focus on firstly MEMS-actuated Solid-State LiDARs. We use here a 2-axis MEMS-actuated LiDAR from Blickfeld as an operating sensor. And this LiDAR mainly consists of one laser emitter and receiver and 2 MEMS-actuated mirrors that oscillate to reflect the beam. And with that technology, the LiDAR achieves a field of view of around 70 to 30 degrees. Thereby, the horizontal mirror oscillates in a harmonic continuous curve that determines the horizontal field of view, and the vertical one has variable amplitude, which thus creates the conical scan pattern we will see later on. As a second point, we further tackle the irregular format of point clouds with a voxel-wise approach, meaning that we divide the 3D space into a discretized volumetric grid and fuse points into these voxels to get it processable. The main problem with voxelization is that this approach always goes in with information loss, and we lost or abandoned the 3D topology of the 3D point cloud. This behavior was mainly the starting point for our research work, where we mainly aim for reduction of this for this behavior. And last but not least, we focus on crowd analysis, where surveillance scenarios often comes with occlusions, which as I already said, is a persistent problem in 3D point cloud perception, and yeah, it's also adaptable to a large variety of other fields like robotic bin picking, something like that. And these occlusion effects can be seen here. Example, even for us humans, it is hard to distinguish if this is one person or two. And yeah, turns out actually 3 person with a heavy information drop. That person here in the back, you have only a very few points left. And consequently, we need methods that meet this demand for fine-grained prediction capabilities. And based on this, we made the hypothesis that we, when we incorporate the geometrical description of the scanning system, we can reduce the information loss while voxelization, and that we can reduce the computational effort because our system becomes easily scalable. For solid-state LiDARs in special, or our sensor in special, that means that we must incorporate the non-uniform density of the beam distributions, where at the corners, much more beams are emitted on a smaller 3D space. Based on this, and to investigate our hypothesis, we firstly needed to generate a solid-state LiDAR dataset with heavy occlusion effects. Since there's nothing comparable open source available, and we used Tala, which is kind of an automotive simulator, to generate synthetic data of such surveillance scenarios. And the code for that will be made open source available to close this lack of sensor diversity. We further proposed a voxel-based semantic segmentation network that consists mainly of an encoder-decoder core of sparse convolution layers. And lastly, and most importantly, we proposed the scan pattern adapted voxelization method that is tailored to MEMS-actuated LiDARs. So, as mentioned, we propose a data generation pipeline with which we generate a total of 80,000 point clouds, annotated point clouds of unique scenes. And we therefore distributed the LiDAR uniformly on a radius varying hemisphere, and captured each scene from around 100 different viewpoints. And for the scenery, we sampled a random number or random amount of people with different densities in realistic surveillance scenarios. The result can be seen here, where we have annotated point cloud, and it's really good to see that we have a wonderful scan pattern. For the voxelization itself, we proceed twofold. So, given the fact that our solid-state LiDAR emits the laser based on the steering angles of the MEMS-actuated mirrors, we represent the point cloud, or it seems viable to represent point cloud in spherical coordinates. Secondly, we make use of the fact that the mirrors are the mirror movements are from sinusoidal MEMS dynamics, which is time dependent. So with that, we are, and the given LiDAR configurations, we are able to determine the exact time for each beam. And with that, we are able to get the vertical resolution for each beam index in the horizontal scan line, which allows us to reduce the 3D space we want to voxelize to the area where reflections actually can occur. Next, I want to give you a short overview of our segmentation network. For the evaluation of our method, we used 4 voxelization methods. So we incorporated firstly the cubic partition, which is the common approach, here depicted on the upper left side. Further, we investigated the effects of cylindrical partition, where which respects the horizontal angular emission of the horizontal beam, and further a spherical and the absolute scan pattern adapted approach, where we respect the angular, horizontal, and vertical beam emitting while incorporating the variable vertical amplitude. Our network in general accepts raw point cloud as input. We enrich it with handcrafted features so that we have a 9-dimensional point feature, and these features are initially assigned to the voxels they are corresponding to, and are then processed by pre-MLP layers. With these learned point features, we fuse the points into the corresponding voxels and apply our sparse asymmetrical 3D encoder-decoder core to generate on these voxel features. From the encoder-decoder core, we get voxel-wise predictions, which we can reassign to each point with the voxel point lookup table, and thus get a point-wise semantic classification. For the results, we evaluate on approach twofold for the different voxelization methods with the same network. Firstly, we calculate the mean intersection of a union to investigate the point-wise segmentation performance. And from that, we can see that our approach outperforms the other voxelization methods on this metric. And it is worth to mention that we have a significant performance boost, especially on small objects, which yields some potential for crowded scene analysis or bin picking. And last but not least, we calculated the entropy for the resulting voxel grids to highlight the reduction of that information loss. And here it can be seen that the incorporation of scan pattern adapted voxelization yields even this reduction of information loss. So we can finally sum up that we show that scan pattern adapted voxelization reduces information loss and boosts the extraction of perceptual information. With that said, I want to thank you for your attention, and